Hello, my name's Mr. McQuire and welcome to the first lesson in a sequence of lessons which are on the subject of forces. Today's lesson is about contact forces and friction, and this follows on from work that you've done at primary school at Key Stage 2 when you have compared how things move on different surfaces. You've also looked at forces that are contact forces, and there's one on the slide in front of you, but also non-contact forces such as putting two magnets near each other. Now you're going to need to get some equipment for today's lesson, so you may need to pause this presentation at this point to be able to do this. First of all, you need to make sure you're somewhere that is quiet, free from distractions if you can find that. And you will need a pen and paper. But in addition to that, you will also need to find a ruler, possibly a 30 centimeter longer one, pencil with a point, dinner tray or something that's a sloping smooth surface, and then I'd like you to find either yours or belonging to someone else several shoes of the same size but are different types. So for example, a school shoe and a training shoe, maybe shoes that belong to different sports, or even perhaps if you wear shoes for dance or rock climbing, walking boots, pit boots, but they must be the same size. That's just a little piece of work that we're going to do later in this particular presentation. So if you need to pause the presentation and get some stuff together, please do that now. So let's get our minds moving and see if we can recall some information from previous learning. If you look at the three pictures you've got in front of you, all of them are from a fairground, but all of them show the use of forces. I wonder if you could spend 60 seconds just looking at the images, see how much you can recall about forces and where you can see forces taking place in this particular diagram. Okay, so let's do some thinking for a second, see if you can recall things. Now, this person here on the slide image, let's see if we can put this on. So I'm now wiggling an image on it. Set off from the top. I wonder if you know what force it is that's brought that person downwards, and I'm hoping you're thinking of the word gravity now. It also applies to these people here who are busy dropping very quickly. You can see their legs being lifted out as they drop downwards using the force of gravity. Now these people here, there are push and pull forces going on here, the pull of the chains, their hands gripping and pulling on the chains as well as they go round and round. Obviously they're up high in the air as this lifts up, so we also have forces of gravity, and we have them hitting the air as they move as well. So we can talk about forces perhaps like wind resistance, you may know, but also a force of friction as they move, and we've certainly got friction forces on this slide as well. So hopefully those are words that are not unfamiliar to you, and we're going to explore those in more detail as we go through this presentation today. So our learning outcomes for today then. The challenge is to be able to use arrows to represent forces and to measure friction. That's a piece of practical work. And the aspire is to be able to represent the size of forces using arrows, which will be drawn to scale, and explain what causes friction. So that will be right towards the end of today's presentation. So we've got a lot to do. Let's just keep moving. Okay, so let's start generating some notes for today's lesson. On your paper, in the middle of the top of your paper, put the title down, please, which is Contact Forces and Friction. If you start doing that as I speak to you, that will save some time. Contact forces and friction. Now we're going to ask a couple of questions that are really very basic. First of all, what is a force? Okay, and what can it do? So let's look at the answers of those. First of all, a force is a push or a pull. Very basic and very simple, and we're going to put that down under the title. So once you've finished your title, if you can just write that sentence down, a force is a push or a pull. And then applying that to an object. So what can those push or pulls do? It can change the shape, speed, or the direction of travel of an object. So I'd like you to put that down as well. I'd like you, when you finish, maybe just spend a second thinking about how a push force with a hammer could change the shape of an apple, for example. How it could change the speed of movement of a rolling ball with your foot, or the direction of travel. Same again with a football. So I'm going to give you 60 seconds to put the title down and these basic definitions here: push or pull, and shape, speed, or direction. Okay, so let's have a look then, and just a brief recap. You've got a title and you've got some basic statements about what a force is, but also what a force can do. So let's apply that now in the lesson. Okay, we've got on the right hand side a picture of a Newton meter. Now we would spend some time just getting you to do some assessment about which Newton meter scale to use. So these keys are quite light compared to this clamp that we've got here, and these particular scales measure different amounts of newtons. It's like thinking about, for example, the kind of scales you would use to measure the weight of an elephant compared to the weight of yourself, and you would have to pick the right one. So we will measure the size of a friction force of different objects. We're going to use a tray and several objects to measure the size of the force. And here's the important part: the unit that we use when we measure forces is the Newton, which is a capital N. Now it's Key Stage 2 information, but what I would like you to do, if you didn't know that particular information about the size of a force, then just write the word Newton N down at the bottom of your definitions, or the size of force is measured in newtons. Okay, if you need to pause the presentation to do that, then do that now, but you should know that information already. Force is measured in newtons. Okay, so pause, or we'll just continue with the presentation now. Okay, so what I would like you to do is to take the tray that you have got, something you might eat your dinner off, for example, or maybe a piece of wood or a shelf from a cupboard, and you need to take a pair of shoes, just as the picture is showing up here, and put them at the top of this piece of wood. Now, at the moment, that should be laid flat. And what's going to happen is, using your hand, you're going to lift up the piece of wood until the pair of shoes, or a single shoe would do, starts to slide down the piece of wood. Now, why is it starting to slide? Well, the answer is, of course, that we're adding gravitational energy as we lift it higher and higher using our hand. And at that point then, when the gravitational energy is greater than the force of friction, the shoe will start to slide down the slope. So what we're going to do is a simple investigation to look at which pair of shoes that you've got has the largest amount of friction. Now, the way that we measure that is then to use a ruler and to record the height that we lifted the wood to before the shoe started to slide. So let's just go through the diagram again. Here is the ruler, here's the surface, tray or a shelf or something that we're using. Then we've got a shoe that we have placed on there of one type. Now, obviously, if you then move to another type of shoe, I need you to keep the size of shoe the same, because these are variables that we need to keep constant. They're called control variables. The only thing we're looking at today is how different shoes have different amounts of friction. We have to keep the surface the same, for example, as well. So here's some instructions. Place the shoe on the tray, lift the tray until the shoe just starts to move. Record the height of the tray in centimeters using your ruler, and then repeat with a different shoe. So I'd like you to find, I hope, maybe 3 different types of shoes that are the same type. So it may well not be your shoes, that somebody in your house has more shoes or types of shoes than you do, or maybe you have several pairs of shoes yourself. Now we're going to record the results, and I'd like you to move on to the next slide if you understand exactly what I've just said, or just rewind the last minute or so and re-listen to the instructions for the practical work. So on your piece of paper, here is a results table, something like this. I'd like you to put into your notes. We've got the object, which is perhaps a school shoe. Now, my shoes are size 8, so that would be size 8. I might have a pair of sports shoes, which again would be a size 8. Now, different types of shoes, I've been thinking about that. I've got boots, for example, so I would put walking boots down here that would be size 8. Perhaps if I did some kind of dance, I might have dance shoes that might be a size 8 as well. And then I'm going to write down here just a number, and that's the force that's in size of the friction force that's represented by the lift in centimeters. So that may be 15 centimeters that I had to lift it up. That may be higher or lower than that. The size of the table depends on the number of types of shoes that you have. So what I'd like you to do is to stop the presentation, just pause it here, and use my outline of a table. You need to put the number of lines, depends on the number of varieties of shoes. You may only have 2, a school shoe and a sports shoe. Well, that's fine. Okay, and I would like you then to record which one of them has the highest friction force, because it has the highest centimeters. This column here I'd like you to put in. We're going to come back to that later in the lesson to complete that. When we look at our Aspire, We're going to represent the size of the force using arrows. So pause the presentation now to do your practical work. I hope you enjoy doing that, and just to write down the height that you lifted it to in that particular box there for the school shoe, and there for the sports shoe, and any other types of shoes in the lower boxes here. Off you go. So now we have a set of numbers that have been collected, and they've been turned into a bar graph. Now, if we have time to do that later in the lesson and you are in school, then someone may help you with that, but we're not going to concentrate on that today. We're going to look at the results that you have got and just see if we can interpret the results and say what we have found. Now, looking at my results, I can say that the shoe that has the most friction, I wonder if you can get there ahead of me, the shoe with the most friction is the Rock shoe, which is a very sticky shoe. It's got a continuous surface on it, a bit like the surface of a table tennis bat on the bottom. It's very sticky, and we had to lift it to 5 centimeters to start that particular shoe sliding on the surface that I used. The one with the next friction is a training shoe, and coming up at the back, very hard soles of my school shoes, and they're not very good and grippy at all, especially in the snow, and we're going to come back to that particular idea later. Now, I'd like you to do a little bit of writing underneath the table where you have got some results now from your own shoes. I'd like you to just spend 60 seconds and to do a little bit of conclusion work. What have you found? Which shoes have got the most friction? So I'd like you to start off with a sentence, for example, I found that, and then just write down which shoe had the most friction with the word because afterwards, and just tell me about the height that you lifted it to, and then do the same for the other shoes that you have, finishing off with the least friction shoe that you have on there. So you've got 60 seconds just to see if you can write a quick couple of lines of a conclusion under your table. Very good. So we should now have a description of the results table that you have. Obviously, people who design shoes are very interested in the kind of experiments that you've done, and they do similar experiments in laboratories for well-known shoe companies that you would go and pick shoes from to make sure that they've got the right amount of grip for a particular sport. Some shoes, of course, need massive amounts of grip, such as sprinters, and they would even go as far as having spikes in the bottom of their shoes to ensure that they didn't slip at all as they moved off. So we're now going to look at the challenge a little more, to be able to use arrows to represent forces. And as we can see here, we have a picture of a cyclist. Now, that particular cyclist, as you can see, has got 2 arrows underneath the bicycle. The first arrow under the front wheel is bigger than the arrow going backwards, and the size of the arrow is very important. We're moving on to the Aspire straight away here. It's important because it allows us to describe which of the forces are bigger. Let's just look at that for a second. First of all, the force for going forwards is coming from the cyclist's legs. The force going backwards is wind resistance, because the person, as they begin to go quicker, hits more air particles, and that tries to slow them down. It's wind resistance, friction in the air. And in this instance, the force pushing forwards is bigger than the wind resistance holding them back. So from this diagram, this tells me that this cyclist here is accelerating or getting quicker. Now, I wonder if you could think for a second what it would mean if the size of these two arrows was exactly the same. Now, I hope that you're thinking that the person would be traveling at a constant speed, because the push force of the cyclist using the legs and the friction force of wind resistance would be the same, so therefore their speed would be constant. Now, we can use these diagrams repeatedly in this topic, and you're going to be doing that in future presentations that we cover. Okay, so let's look at another example. The diagram in front of you here has been drawn to scale. We've got a pull force of these three people on this side of 400 newtons, and we've got a pull force on this side of 300 newtons. Now, I'm hoping that you could tell me straight away who would be winning this tug of war. Not just because of the way the diagram is drawn, by the way, because that should help you anyway. So hopefully you're going to tell me that these guys here are winning because their force is 400 newtons. You can see they're still pulling, whereas these guys have had to stop pulling because they've been pulled too hard, and they're all going to the left at the moment. Now, if you're feeling very clever, if we made each 100 newtons worth 1 centimetre, then this arrow would be drawn to scale and would be 4 centimetres long. And that would make, I'm waiting for you to fill in the gap here, how long would this arrow be? And hopefully, if 100 newtons equals 1 centimetre, then we would need to draw this with a ruler at 3 centimetres long. Now, in future lessons, you're going to start talking about the kind of leftover force when forces aren't balanced. And there is a leftover force, a resultant force, so we would say in this particular diagram. And we've got 400 here and 300 here. We know it's going that way. So if you're feeling very advanced, we could say that it was going to go to the left with a resultant or leftover force of 100 newtons. Now, it's going to be your opportunity to apply that in a second. Okay, here's another example, and I want to use this example to get you doing a little bit of extra work on your results. Draw force arrows for each of your materials with 1 centimetre showing 1 newton. Now, here's an experiment that students would do in class. We give them different materials and they stand the same object on top of the materials and then use a Newton meter that you saw in one of the earlier slides, and they pull on the Newton meter until it starts to slide. So it took 5 newtons to make this object, which is the same for all of these tests, start to slide. So therefore this arrow, 1 centimeter equals 1 newton, here's the scale, is 5 centimeters long. Okay, now you can see that we've then got 3 centimeters here and just 1 centimeter for these two. So this is a kind of a graphic that we can use to very quickly pick out the top result in terms of friction, and that's carpet, which has the most friction. I'd like you to look at your results for your shoes. I don't want you to draw lines for how many centimeters you lifted the board up or the tray to get the shoe moving, because I'm going to guess that you might have some very, very long arrows that you draw at this point, which I don't want you to start taking up lots of pages to draw. What I would, however, like you to do is just to write down how many centimeters you would draw the arrow if you had space to do that. Now, that's going in the third column that I left for you in the previous slide, where you should have written your results in the middle column. So I'd like you to spend a minute just writing down the size of the arrow that you would draw in centimeters if I had space and could speak to you personally to get you to draw those. So if you could spend a minute just looking at it, let me help you a little bit more. If your shoes for school took 8 centimeters to lift, and we had 1 centimeter equals 1 Newton, then I would obviously draw a line that was 8 centimeters long at this point. Now, we don't have a Newton meter, but we just have the lift of the tray to help us show the friction. So just write down the same number again that you've written down for the results. Now, if you've got space, maybe perhaps you're following this lesson in school, then you may have time to be able to draw those results properly with the length of the arrow showing your results accurately. Okay, now I'd like to put a subtitle, please, of friction, which I have underlined up at the top. I'm going to go through this and then I'm going to move on to the next slide, and I'm going to ask you to explain what friction is. You may use a diagram, but it's really important that you listen very closely, because we're nearing the end of our lesson today, and I would like you to be able to write independently, having listened to what I say. So let me run through this. First of all, I want to start with the diagram. We have got something like a brick sat on top of some concrete. They may look quite smooth, but when you look at them under a microscope, you see that the surface of the brick is actually quite rough. The surface of the concrete is actually quite rough. So you can see that they interlock, and we are describing here the friction and how it occurs. So let's look at that. Friction is caused by two surfaces that are not completely smooth pushing past each other. So you can see there's a force here pushing the brick on top of the concrete. The surface irregularities, bumps would be a nice word as well, get stuck and they cause friction, a contact force that opposes motion. So we've got a push force here that makes the brick move, and as that brick moves, trying to oppose the motion, the opposite, opposing, down here in our keywords, the trying to push the other way is friction. What causes that friction? How rough the surface is. Okay, now I don't want you to just copy down aimlessly what's written there, because I'm not going to give you time to do that. I will, however, just run through this as an example. We've already got the title of friction, please remember that. We've got a shoe here that's on the ground, and we've got another shoe here that's on the ground, but this time the ground is wet. It says the word lubricant there. So it could be snow, it could just be wet, or perhaps somebody has, heaven forbid, dropped something on the floor in the dining hall and you have stood on it, maybe some food, and you have skidded along the ground. Now, why did you suddenly slide? Well, I hope that you can see what that water, or maybe, heaven forbid, a banana skin may have done in terms of the irregularities that there are on the bottom of the shoe and the ground. That means that you have much less friction and you would slide. Okay, so I'm now going to give you a couple of minutes, perhaps with a diagram that may help you. I'd like you to explain what causes friction. So off you go. Remember, if you need to rewind to the previous slide, you could always do that and re-listen to my explanation. Okay, just a reminder, you should be talking about the surfaces and the forces and what it is that causes that friction to occur. The big word that maybe you're trying to remember was irregularities or bumps. Okay, I hope you jumped appropriately. Now, you should, of course, have been writing about surfaces that have irregularities on them and a push force that is big enough to overcome those irregularities, makes them slide over each other. But the force that tries to stop that push force is called friction. So let's look at the outcomes for today. First of all, to be able to use arrows to represent forces. Remember, the size of the arrow dictates the size of the force that we're looking at. And we have measured friction, but we've not done it using a Newton meter because of where we are. Hopefully you've joined me in measuring it using a slope that's allowed you to spot the point when friction has been overcome and it started to slide. For our Aspire to be able to represent the size of a force using arrows, we certainly thought about doing that today and seen it, but they are drawn to scale and explain what causes friction. And we have spent some time thinking about the word irregularities. Thank you for sharing with this presentation today, and goodbye.